Have you ever wondered how microchips, the brains behind our devices, are made? These tiny pieces of tech are integral to our daily lives, powering everything from our smartphones to our cars. They may be small, but the process to make them is anything but. Microchips, also known as integrated circuits, are composed of millions, sometimes billions of transistors, resistors, and capacitors. These components work together to process, store, and transmit information, making our devices smarter and our lives easier. Creating these micro marvels is no small feat. It requires a blend of precision, complexity, and high-tech machinery. The process, which we'll explore in the coming scenes, involves designing the chip, producing the wafer, creating the circuit pattern, building the layers, and finally testing the chip for performance. So buckle up, tech enthusiasts, as we journey into the fascinating world of microchip production. Get ready to delve into the intricacies of microchip production. Every microchip starts with an idea, a design. In the world of technology, design is king. It's the foundation, the blueprint, the roadmap guiding us towards the creation of a fully functional microchip. The design process is a complex dance of engineering, creativity, and precision, a bridge between the realm of ideas and the physical world. Engineers, the unsung heroes of the microchip world, are the ones who kickstart this process. Using advanced computer design software, they painstakingly create the layout for the microchip. This isn't a task for the faint of heart. It requires a deep understanding of electrical circuits, an eye for detail, and a whole lot of patience. The layout they create is more than just lines on a screen. It's a miniature city of circuits, each with its own purpose, its own function. The engineers must plot out the paths for electrical currents, design the gates that control the flow of these currents, and ensure everything is connected in just the right way. The design stage is of paramount importance. It's here that the functionality of the final product is determined. If there's a flaw in the design, the microchip won't work as intended. Mistakes can lead to errors in data processing, or even complete system failures. Engineers must also consider the physical constraints of the microchip. They have to create a design that fits into a tiny silicon chip, often no larger than a fingernail. This is a world where millimeters matter, where the difference between success and failure can be measured in micrometers. Despite these challenges, the rewards are worth it. A well-designed microchip can process data at lightning speeds, power our favorite gadgets, and even help to solve some of the world's biggest problems. In the end, the design process is a testament to human ingenuity. It's a blend of art and science, a marriage of form and function. It's a process that takes us from the abstract to the concrete, from the world of ideas to the world of physical objects. Once the design is ready, it's time to bring it to life. The actual production of a microchip begins with a simple, yet crucial ingredient: silicon. Silicon, a naturally occurring element, is the second most abundant substance on Earth, beaten only by oxygen. Its atomic structure makes it an ideal material for semiconductor devices. Think of it as the canvas on which we'll paint our masterpiece, the microchip. The process starts with a cylindrical piece of silicon, known as a silicon ingot. This ingot is sliced into thin discs, or wafers, each less than a millimeter thick. These wafers are then polished to a mirror-like finish, creating a smooth and flawless surface. It's a meticulous process where even the tiniest speck of dust could cause a defect in the final product. That's why microchip fabrication facilities, or fabs, maintain an environment that's about 1,000 times cleaner than a typical operating room. Now, let's move on to the fascinating process of photolithography. This is where the magic begins, where we start to breathe life into our silicon canvas. Photolithography is a process that uses light, or more specifically, ultraviolet light, to transfer a circuit pattern from a template onto the silicon wafer. The wafer is first coated with a light-sensitive material called photoresist. It's then exposed to ultraviolet light, which is passed through a mask that carries the microchip design. The exposed areas of the photoresist harden, while the unexposed areas remain soft. These soft areas are then washed away, leaving behind a precise imprint of the chip design on the wafer. This intricate process is repeated multiple times, layer upon layer, to build the complex architecture of a microchip. It's kind of like building a skyscraper, but on a microscopic scale. With the chip design imprinted onto the silicon wafer, we're ready for the next step, but we'll save that for the next scene. Stay tuned, and don't forget to hit that subscribe button if you're finding this journey through microchip fabrication as fascinating as we do. Now we enter the phase of etching and doping. In the world of microchip manufacturing, etching is the process where unwanted silicon is removed to reveal the intricate design of circuits and transistors. This is a critical step in the creation of a microchip, much like an artist chiseling away at a block of marble to reveal the masterpiece hidden within. Etching begins with the application of a layer of light-sensitive material called photoresist onto the silicon wafer. The wafer is then exposed to ultraviolet light through a mask that outlines the circuit design. The exposed areas harden, while the unexposed areas remain soft and are washed away, leaving behind the blueprint of the chip's circuitry. Next, the wafer is bathed in a chemical solution that etches away the unprotected silicon, creating valleys and trenches. These carved-out areas form the pathways that electricity will travel through in the finished microchip. The hardened photoresist is then removed, leaving behind a silicon wafer etched with the intricate circuitry of our microchip. Right on the heels of etching, we find ourselves in the realm of doping. This is where impurities are introduced to modify the silicon's properties. Depending on the type of impurity introduced, silicon can either become a P-type with positive charge carriers or an N-type with negative charge carriers. This process of adding impurities is critical because it allows us to control the electrical properties of different areas of the chip, which in turn allows us to create the transistors that are the building blocks of the microchip. These doped regions, when combined with the etched pathways, form the basis of the transistors and circuits that give life to our microchip. Each transistor can switch between on and off states, representing the ones and zeros of binary code, the language of computers. Etching and doping lay the groundwork for the microchip's functionality. We've now seen how these two processes help transform a simple wafer of silicon into a complex network of circuits and transistors, the heart of every microchip, and the driving force behind our digital world. We're nearing the end of our journey with just a few steps left. It's been a wild ride so far, hasn't it? Now, after all the designing and producing, we've arrived at the stage of metallization. This is where the magic really starts to happen. Think of metallization as the final touch in a masterpiece painting, where the colors begin to connect and form a coherent picture. In the world of microchips, this step involves adding metal layers to the chip, forming an intricate network of pathways for electrical currents to flow. It's like creating an elaborate city map, but on an incredibly small scale. Now imagine you've just built a beautiful sandcastle, and you want to protect it from the harsh elements. You'd probably build a barrier around it, right? Well, that's exactly what happens in the next stage, packaging. The delicate chip is encased in a protective shell, safeguarding it from the outside world. This shell is not just any old casing, folks. It's specifically designed to withstand a variety of conditions, protecting the chip from heat, cold, dust, and even the occasional coffee spill at your office desk. But we're not done just yet. After the chip has been packaged, it must undergo rigorous testing. This is the quality control phase, where each chip is tested for functionality and performance. It's like a final exam, where the chip must prove that it's ready to take on the tasks it was designed for. And after all that designing, producing, metallizing, packaging, and testing, what do we have? A tiny piece of technology that's ready to power our world. From your smartphone to your car, these microchips are hard at work, ensuring that our daily lives run smoothly. And voila! The microchip, the result of a complex and meticulous process, is ready. It's a testament to human ingenuity and the power of technology. A tiny marvel ready to help us explore, create, and connect in ways we could only dream of just a few decades ago. From a simple silicon wafer to the brains of our devices, the journey of a microchip is truly fascinating. We've gone from the bare beginnings with design, all the way through the meticulous and intricate stages of production. The transformation of a mere speck of silicon to a complex microchip capable of powering our favorite gadgets is a marvel of modern technology. This process, combining human ingenuity and cutting-edge machinery, is a testament to our relentless pursuit of innovation. It's an intricate ballet of design, engineering, and precise execution that brings to life the tiny, yet mighty, microchip. If you found this journey through the world of microchips as captivating as we did, do consider giving us a thumbs up and hitting that subscribe button. Sharing this video could help spread the wonder of technology and maybe inspire the next generation of innovators. Thank you for joining us on this journey. See you in our next video.